Great. There's still a couple more people trickling in, but I think we will start. So hi, everyone. Thank you very much for joining us this morning, this afternoon, wherever you are. And this is the third webinar as part of the CIWEM series that we've been running here at Fathom. So some of you may have joined us for our two previous webinars where we talked about modelling flooding on a global scale during the first one. And then in the second one, we discussed how climate change might impact flooding in the future. And the recordings of these webinars can be found online, and I think the links have just been posted in the chat panel now. So if you're interested in either of those topics, then please go and check them out. And today we'll be discussing compound events and how they come into play in risk assessment. Next slide, please, Joshua. So my name is Natalie Lord. I'm Principal Climate Scientist here at Fathom. And I'm joined by Joshua Green. So he's a PhD researcher at the University of Southampton, and he's studying compound flooding and also collaborating with Fathom as part of that project. Next slide, please. So this is the general agenda that we'll be following today. So I'll give a short introduction to Fathom. I'll then hand over to Joshua to discuss what compound events are, along with some examples, what methods we can use to understand them, and also to what extent hazards and extreme events are connected regionally and globally. I'll then discuss some of the impacts that climate change is having on extremes and compound events. We'll then talk through tropical cyclones as a specific cause of compound events, a specific driver, and how these compound hazards can be modelled. I'll then give some examples of how knowledge about compound events can be applied to engineering uses specifically, and then we'll finish with some key takeaways and a question and answer session. So please, if you do have any questions throughout, add them into the Q&A box. There's one on the bottom of the screen, and then we'll be able to answer them at the end. Next slide, please. So these are the intended learning outcomes for this webinar. So you should be able to, by the end of the webinar, hopefully, explain what compound events are, understand the difference between compound flood and other compound hazard events, establish to what extent events like flooding and wind are connected in different regions, and also understand how compound events and their impacts can be modelled, and then possible applications of this type of data. Next slide, please. So a bit of background on Fathom as a company. We were formed out of the University of Bristol Hydrology Research Group, and our main aim is to provide water and climate risk for the entire planet. So we work across a range of different markets, which includes insurance and financial services, governments, NGOs, and then of course engineering and the built environment. And research has always been a really important part of our company development. So many of the science team have previously worked at universities. And it's why we still collaborate with researchers and PhD students like Joshua at various universities around the world. And we also aim to publish our models and our data sets in peer-reviewed scientific journals as well. Next slide, please. So on to the main part of the webinar. I'll now hand over to Joshua to talk us through what we mean by compound events.
Thank you for the introduction, Natalie. As mentioned, my name is Joshua, and I'm a PhD student at the University of Southampton, researching compound flooding. To start off, what is a compound event? There are a variety of perspectives. Oops. Let's see. There are a variety of perspectives, but the three most dominant definitions are as follows. In 2012, compound events were formally defined for the first time in the IPCC Special Report on Climate Extremes as 1, 2 or more extreme events that occur simultaneously or successively, 2, a combination of extreme events where conditions amplify the impact, or 3, a combination of non-extreme events that together lead to an extreme event or impact. Then, in 2014, Leonard et al. Present a different definition. While they agree on the requirement of multiple variables or events, they take a more strict perspective, arguing that compound events require both an extreme impact and statistical dependence between variables or events. Thus, two independent events that happen to co-occur or combine would not be considered a compound event under this definition. And third, most recently, Zeichler et al. 2018 proposed the broadest definition, stating that compound weather and climate events can be any combination of drivers, variables, or hazards that contribute to societal or environmental risk. Under this perspective, the events of interest do not have to be extreme or statistically dependent. This definition, however, restricts compound events to only natural weather and climate-related drivers. Compound event-based practices may consider a variety of different drivers, events, and variables. On the left are many of the weather and climate events commonly considered in compound event research, including precipitation, coastal processes, river discharge, wind, temperature, and drought, just to name a few. While this talk will focus on compound weather and climate events, do understand that compound events can involve any nonlinear interaction of other drivers or hazards, such as those shown on the right, from landslides and earthquakes to health, agriculture, and technology. For example, wildfire, pollution, and health, or flood, heat wave, and disease. Following their 2018 definition of compound events, Zeichler et al. 2020 proposed a compound event typology framework, defining 4 different interaction types. 1, preconditioned compounding, where pre-existing conditions amplify in an event. 2, multivariate compounding, involving multiple interacting events. 3, temporal compounding, where one event follows another. And 4, spatial compounding, where events occur in the same locations. These types are non-exclusive, meaning multiple types can apply to the same event. In the next few slides, I will discuss 2 example compound events that demonstrate different combinations of these interaction types. First is Hurricane Harvey, which was a highly destructive Category 4 tropical cyclone that made landfall in Texas and Louisiana in 2017. Harvey was notable for its extreme winds and for being the wettest tropical cyclone to affect the United States, with over 60 inches of rainfall. Harvey is a great example of a compound event, as multiple flood drivers combined to produce more severe flooding than their individual components. Winds and rainfall interacted to produce atypical storm surges along the coasts and estuaries of Texas, and compound flooding in the Houston region. Peak flooding occurred from combination of ocean wind and corresponding surge, plus the rainfall-related discharge of the Buffalo Bayou and San Jacinto River. In this figure from Hung et al. 2021, we can see the relative contribution of A, surge, B, river, and C, rainfall. As expected, the maximum disturbance ratios reveal that the extreme rainfall was the largest contributor to compound flooding. Here, we can also see regions of positive compounding, shown in red, with significant compounding in the East and West Bays, Upper Bay, and watershed areas with river network. Furthermore, this study determined that simply adding together the individual flood components would have overestimated flooding in many areas by at least 20%. For the second example, we go to the summer and fall of 2021, during which North America's Pacific Northwest region experienced several sequential extreme hydrometeorological events. In the summer, British Columbia, Canada faced compound dry, hot conditions and fires, with global record-setting heat domes reaching a staggering 50 degrees Celsius, causing several towns to burst into flame. In the fall, these periods of heat and fire were then followed by atmospheric river-driven extreme rainfall, dropping a massive 500 millimeters rain in just 2 days. This resulted in catastrophic flooding of the BC Fraser Valley. Due to the preconditioning compound hot-dry to rain-flood, this was the most destructive event in the history of BC, causing 5 to 7.5 billion in damages. The resulting flooding blocked off all highways and railway transportation to Western Canada, destroyed thousands of farms, and killed millions of livestock. Following these previous examples, you might ask, well, how are events like drought, fire, and flooding linked? Or how are extreme heat and flooding linked? First, drought and fire both change the properties of soil, such that hard and dried soil prevent water absorption, and fire ash creates hydrophobic layers on the soil surface. As a result, water from rain or rivers is unable to seep into the ground and instead flows rapidly across the surface, causing flooding. Next, heat is related to flooding, as air temperature directly influences atmospheric water vapor and thus rainfall. According to the Clausius-Clapeyron relation, for every 1 degree Celsius increase in temperature, the atmosphere can hold about 7% more water. Due to these inherent Earth system dynamics, compound events involving these above processes are common. Now, we will change focus and briefly introduce compound flooding. In the past decade, there has been growing focus on compound event-based perspectives for risk assessment and hazard management. Compound flood research in particular has seen rapid development. In the figure on the right, we can see the vast majority of all compound flood research has been published in just the past few years. Compound flooding involves the consideration of multiple flood drivers, including rainfall, river discharge, storm surge, wave action, tidal oscillation, and groundwater levels. A recent global study by Islander et al. 2020 estimates that 9% of coastal populations are at elevated risk for compound flooding, and that 20% of global estuaries are dominated by compound river surge interactions. Here, we've only provided a brief glimpse into compound flooding, but if you're interested in learning about compound flooding in greater detail, I encourage you to check out a recent review paper I've written, synthesizing the state of compound flood research in coastal and estuarine regions. Next, we'll turn to risk assessment. Traditionally, risk assessment has considered the mechanisms and drivers of hazard events individually. However, we know that multiple drivers can result in extreme events, even if the drivers themselves are not extreme. Well, why does this matter? Overall, societal risk is greatly underestimated when the synergistic effects of compound interactions are not considered. In the conceptual figure below, we can see that the sum of the risk from individual drivers is less than the total risk for a given hazard scenario. Thus, if there's one point to emphasize, it is that risk assessment must account for compound interactions. Well, how do we go beyond this conceptual diagram? How do we know this is true? Here are 3 recent studies that quantify how compound flood risk is underestimated. First, Zhang and Chang 2022 revealed that failing to consider the combined interactions of pluvial coastal flooding would increase the number of missed or false flood alarms in Taiwan. Khalil et al. 2022 found that considering flood drivers separately would underestimate water levels by 62 and 12 centimeters in Jindalee and Brisbane, Australia. Finally, Santos et al. 2021 estimate that compound fluvial, pluvial, coastal 1-year return periods were 15 to 35 centimeters higher than non-compound estimates in Sabine Lake, Texas. Now, I'll briefly introduce approaches for understanding compound events. Overall, there are three methods. One, statistical modeling and analysis. Two, numerical physics-based modeling. And three, hybrid modeling, involving a combination of both statistical and numerical approaches. There is more to discuss than we have time for today in terms of methodology, and I'll only be providing a very high-level overview. If you're interested in more detail, I again encourage you to check out the review paper shared earlier. We'll start off with statistical modeling, which typically, but not always, involves some variation of the three techniques listed below. One, dependence analysis. We can understand compound events by examining the dependence between two or sometimes three variables. This is done using various correlation coefficient or copula functions, which reveal how variables influence each other at extreme percentiles. Second is joint probability approaches. This involves extreme value analysis and Bayesian probability. Here, we look at the probability of two or more co-occurring extreme events where the variables are at least partially dependent. Third is joint occurrence approaches. This involves counting how many times two or more simultaneous extreme events are observed over a period of time. In this example from Kuasanon et al. 2020, we see the global probability of joint annual maximum river discharge and storm surge for a 5-year return period. The greatest likelihood of compound river surge events are in coastal North America, Western Europe, Southeast Africa, Northern Australia, and Southeast and East Asia. This same study also examined the global joint occurrence of river discharge and storm surge using a 3-day window from 1980 to 2014, revealing very similar spatial findings. Next is numerical modeling, where we simulate physical events based on a system of governing equations. Numerical approaches for compound event analysis are used to assess compound hydrological, oceanographic, meteorological, and climatic events. Compound events often involve several different Earth systems. As an example, in my PhD research, I am developing a numerical modeling framework for tropical cyclone-driven compound pluvial, fluvial, and coastal flooding. Shown in the diagram to the right, my research framework starts by modeling a series of statistical, synthetic, or historical tropical cyclone events. The coastal component of flooding is then simulated with the hydrodynamic models Schism and Sphinx using the tropical cyclone wind velocity and atmospheric pressure forcings. River discharge is modeled by inputting tropical cyclone rainfall into the hydrodynamic surface routing model FUSE. Lastly, compound flooding is simulated with the hydrodynamic model ListFlood FP using the previously modeled coastal and river outputs in combination with dynamic rainfall. For those interested, ListFlood FP is the same model used by Fathom and developed at the University of Bristol by Bates et al. Lastly, we'll briefly cover hybrid approaches. Well, both statistical and numerical approaches have limitations when used in isolation. However, hybrid numerical statistical approaches can take the best of both, benefiting from the computational efficiency of surrogate statistical modeling while maintaining a realistic representation of the physical processes. For example, many compound flood studies first statistically simulate storm events, which are then used to force physical numerical models. This is an approach Fathom takes in creating its flood hazard layer products using stochastic tropical cyclone event sets generated by climate and weather risk partner RIASC. Now, To what degree is there connectivity between events, such as wind, drought, heat, rain, and flooding? And how does this vary at spatial scales? Here, we'll briefly discuss findings throughout the literature. First, we'll focus on Europe, where there's strong connectivity between wind, rain, and flooding. Owen et al. 2021 found that wind and precipitation co-occur up to 50% of the time in Europe. Wind and precipitation are often driven by the same storm events, and areas of Europe with extratropical cyclones account for over 70% of compound wind and precipitation extremes. In the case of the UK, Bloomfield et al. 2023 find that wind, rain, and river flows have correlations of up to 0.8. At the global scale, Martius and Pafal 2016 find that wind and precipitation extremes co-occur over 20% of the time. As seen in the figure and circled in red, compound extremes are most prominent in coastal regions and areas with tropical cyclones, where here, winds and precipitation co-occur 70% of the time. Globally, Ryder et al. 2020 examined compound events related to wet conditions. Compound event hotspots involving rain, hail, wind, and stream flow are prominent in Eastern North America. High susceptibility of compound surge, wave, and wind are seen in coastal North America, Europe, Australia, and East Asia. Furthermore, Ryder et al. 2020 also assessed global compound events involving dry conditions. Compound events involving heat waves are predominant in the mid-latitudes, including North America, Europe, Russia, Australia, South Africa, and Argentina. Additionally, there are high likelihood of fire-related compound events in North America, Australia, and South Africa. That has been all for me. So now I will pass it over to Natalie to discuss climate change and tropical cyclones.
Great, thanks, Joshua. So I'll now talk through some of the ways that climate change may already be impacting climate extremes and compound events, or how they may impact them in the future. So a good starting point is to understand what's going on in the atmosphere. So we already know that humans are releasing large quantities of greenhouse gases into the atmosphere. This is trapping heat, and then this causes the atmosphere to warm up. So from an inland flooding perspective, if we look at along the top panel of the figure, this can fuel much larger and more frequent rainfall events, which can in turn lead to larger river floods. Although this isn't the case everywhere. So if you're interested in more insight into this, if you check out our second webinar, which was looking at the impacts of climate change on flooding globally. From a coastal flooding point of view, global warming is causing sea level rise due to thermal expansion and melting of land ice, so things like glaciers and also ice on the Greenland and Antarctic ice sheets. And this can then combine with processes like storm surges and tidal changes to increase the risk of coastal flooding. Next slide, please. And we can clearly see some of these impacts in this figure. So this is from the latest report from the Intergovernmental Panel on Climate Change, which Joshua has already mentioned. And this analysis shows future changes in what they're referring to in the report to as climatic impact drivers. So essentially climate extremes, which can lead to impacts on humans or the environment. And they look at this across around 50 regions globally. So they split the globe into 50 regions. And these are shown up on the x-axis. So you can just see them numbered in purple and in orange on either side of that black line. And purple indicates an increase in the particular impact driver, orange a decrease, and then the darker colors indicate high confidence in the projected changes. Next slide, please. So we can see that we have high confidence that all regions will experience changes in multiple impact drivers. And if we highlight a few specific ones, which you can see circled by or highlighted by the red boxes, we can see that extreme heat on the far left, heavy rainfall and pluvial flooding in the centre, and relative sea level and coastal flooding on the right-hand side are all projected to increase in the majority of regions with high confidence. So they've got those dark purple bars, which indicate we have high confidence in those increases. River flooding, which is sort of centre left, is also generally projected to worsen in most regions, but there's less confidence in this. There's more uncertainty in how these processes will develop in different regions on a local scale. And fire weather and drought are also, again, projected to increase, but with lower confidence. And then tropical cyclones and severe windstorms are also projected to increase in some regions, but again, with medium rather than high confidence. And I'll talk in a bit more detail about that later on. And these changes in multiple drivers in different regions have implications for risk and adaptation and mitigation efforts. Next slide, please. So if we now look at changes in compound events in specific regions, this paper by Bevacqua et al. Used an ensemble of CMIP5 climate models. So this is kind of the previous generation of global climate models that were run as part of a big comparison project. And they also use storm surge modelling to look at how changes in compound flooding might occur across Europe. So on the left-hand side, they looked at the probability of compound flooding during the historical period, so 1980 to 2014. And they found that the highest probability of co-occurring storm surge and extreme precipitation represented here as the lowest return period. So the sort of reddy orange colours represent the highest probability. These probabilities, are highest around the Mediterranean region. They then looked at future changes in the probability, so on the right-hand side of the panel, and they found that a generally increasing probability or a decrease in the return period occurs across much of Northern Europe. So you can see these kind of red and orange colours along many coastal regions. And they found that the main driver for this increased probability was generally extreme precipitation, so that kind of warmer atmosphere, wetter atmosphere, resulting in more frequent and more extreme precipitation events. But in some regions, changes in extreme sea level and also changes in the statistical dependence of storm surges and extreme precipitation also played a role as a driver. Next slide, please. Bloomfield et al. Looked at compound flooding and wind in the UK and Europe. So they used climate data from the UK Met Office UK CP18 12-kilometre climate model ensemble. And in these plots, they show the Great Britain aggregated correlation between instantaneous wind or 10-metre wind gust and total precipitation. So this is represented by the solid purple lines that you can see. Wind gust and river flow, which is represented by the orange lines. And then the correlation between two indices, which were aimed to be more directly related to impactful extremes. So storm severity index and flood severity index, which are shown by the blue solid lines. And if we look at the left-hand panel, we can see that the highest correlation of around 0.7 is between the instantaneous wind gust and total precipitation at all timescales. So you've got different timescales along the bottom from, a daily timescale up to numbers of months. For wind gusts and total river flow, the correlation is lower at daily timescales, and after that it rises more towards the wind and precipitation sort of correlation values. And then the correlation between the storm severity index, and the flood severity index is lower again. But generally, it does emphasize that the correlation between these most extreme events is evident across Great Britain. When comparing the historical and future periods in UKCP, so looking at the right-hand plots now, there is a small but discernible increase in the correlation between total river flow and instantaneous wind gusts. So this is the orange line again. You can see it kind of moves further up the correlation x-axis. There's also some evidence for increased correlation between the storm severity index and the flood severity index at short timescales out to around a month. And overall, the paper concluded that there is evidence for an increasing probability of co-occurring extremes in the future in the UK. Next slide, please. So we're now going to focus in on tropical cyclones as a driver of compound events. So in terms of the impacts of climate change, there's already evidence over the historical period that changes are occurring in the behavior of tropical cyclones. So this figure, for example, shows total cyclone precipitation in the US for the historical period, so 1960 to 2018. And we can see that the trend for the slope is generally positive around this kind of southern and eastern states, so indicating an increase in total precipitation over this period. And this is due to a number of factors, so an increase in hurricane activity, atmospheric moisture, and then also sea surface temperature, which allows those kind of storms to A, pick up more moisture, but B, develop into more intense storms because they've got that kind of heat source just off the coast that fuels them. Next slide, please. There's also evidence for an observed trend of decreasing cyclone motion. So some TCs are moving more slowly, particularly when they get over land. And this increases the likelihood of them causing storm surge and inland flooding as a compound event. So as they move over a region more slowly, they have more time to essentially drop rain on that region. And recent examples of this have included Hurricane Debbie and Hurricane Harvey, which both occurred in 2017 and were associated with high levels of flooding. Next slide, please. In terms of future projections of changes in TCs, it's generally well understood that precipitation rates will increase globally as the climate warms in tropical cyclones. So if you look at the bottom right panels on this plot, you can see that rain rate on the far right-hand side is generally is positive, and the uncertainty bounds are kind of over that 0% change. So there's good agreement that precipitation rates are going to increase as the climate warms. The intensity of TCs is also projected to increase. So as I mentioned, like higher sea surface temperatures and things will cause stronger storms to develop. And this is then linked to the fact that the proportion of tropical cyclones globally that develop into strong category 4 and 5 TCs is also projected to increase. So there is uncertainty in how the total number of TCs might change. Some models suggest an increase, some suggest a decrease, but generally of the TCs that do develop, more of them are expected to get to those very strong categories. And there are variations across regions, so different ocean basins and uncertainties in some of these characteristics, but those are the kind of headline findings, I guess. Next slide, please. So a recap of the key takeaways from this section. Greenhouse gas emissions are a major cause of the intensification of different climate hazards, from floods, droughts, heat waves, storms. Compound events may increase in frequency and intensity due to anthropogenic climate change in some regions. And then also under a changing climate, the interrelationships and dependence between different variables which contribute to compound events are also likely to change. So it's really important to understand these changes. Extreme rainfall is generally projected to increase, including that associated with tropical cyclones. And we've already talked about how that's related to more frequent and more extreme storm events in many parts of the world. And then coastal flooding is also projected to increase due to this sea level rise, which then increases the likelihood of compound flooding from things like storm surges. Next slide, please. So we'll now talk about how we can model compound hazards from tropical cyclones. Next slide, please. As we've mentioned, tropical cyclones can result in compound hazards. So this may be a combination of or all of inland flooding, coastal flooding, and or wind hazard. And coastal cities are particularly vulnerable to these combined hazards. If we look at the left-hand plot, we can see the return periods associated with tropical cyclones for the historical period. So the probability of how likely it is this region is going to get hit by a tropical cyclone. And we highlighted a couple of the regions in red, which show high probabilities of being hit by a landfalling tropical cyclone. And then if we look at the middle, we can see the middle panel, we can see that particularly these regions where you see these high probabilities, they're also associated with a high risk of storm surge. And also on the right-hand panel, you can see that many of these regions are also associated with a high risk of precipitation. So where both of these hazards are likely to occur, this is where you get those kind of compounding impacts and then the associated damage that comes with those. Next slide, please. So just a small example of this is Hurricane Ida. So this occurred in 2021. It was a category 4 hurricane and was associated with wind gusts of up to 150 miles an hour, which obviously caused a significant amount of damage, maximum rainfall amounts of 15 inches, which resulted in inland flooding, and then also a maximum storm surge of 14 feet. So you can imagine if you have all of these hazards occurring at a site on the coast, then that's going to cause quite a significant amount of damage to the particular asset that you're looking at. Next slide, please. So in terms of factors that influence cyclone-induced rainfall and surge, so compound rainfall and surge, there are many different things that affect tropical cyclones and how severe the precipitation or the storm surge hazard that they cause might be. So for precipitation, these include storm characteristics, so things like the intensity of the storm, the position where it makes landfall, the size, the translation speed are all important. There's also land interference, so the impacts of topography. If you have kind of areas of mountains, that can affect the storm and the amount of rainfall that it drops, and also surface friction as well. Climate change, as we've discussed, will have a big impact. So increases in sea surface temperature and total column water vapor affect the amount of rainfall that can fall, and also the intensity that storm can develop to. Climate variability, not something we've discussed really in this webinar, but we have discussed in the previous ones, but natural climate cycles like El Nino Southern Oscillation, which you may be familiar with, are associated with increases and decreases in kind of the probabilities of things like TCs occurring. So they result in kind of larger scale climate conditions which may be more or less conducive for tropical cyclones developing, so they can have an impact on how many tropical cyclones you might expect in a season, and also how severe they might be. And for storm surge, on the right-hand side, again, the storm characteristics are important. So the things like the intensity, the position, the speed, but also a number of other factors. So things like coastal geometry and also the presence of a continental shelf in relation to the coastline can have an impact on how severe a storm surge might be associated with that event. And so all of this variation means that, firstly, it's really complicated to model tropical cyclones and their impacts, but also that in order to really understand and properly represent the risk associated with these events, you need a really large catalogue of events to kind of model all of these different aspects and to really represent the range and the variety of tropical cyclones that you might expect, both in the present day and in the future as well. Next slide, please. So this is where catastrophe models come in, which Joshua has mentioned previously. And this is where, again, Joshua mentioned, we at Fathom have partnered with a company called RIAST. So they're experts in global extreme weather risk. And we've partnered with them to develop a tropical cyclone CAT model for the US. So starting at kind of the beginning of, I guess, the process that you might go through, we obviously have observations of tropical cyclones that have occurred in the past. So for the Atlantic basin, I think the observations go back to the beginning of the century, although obviously uncertainty in some of the data that are associated with those TCs decreases or gets worse as you go back in time. But realistically, for most of the ocean basins, we only have about 40 years of observations. And if you imagine that you only get a few landfalling TCs every year, so that's really not many events to work with. There would be multiple places on the coast, the US coast, for example, where tropical cyclones haven't hit in the last 40 years, just because it's such a short observational record. But there's no climatic reason why they wouldn't be able to be hit by an event. And so if we don't have observations about that, it means that we don't really properly understand the risk or hazard in those regions. And so this is, it also means that it's difficult to capture the impacts of climate variability. So as I mentioned, you get these kind of annual to decadal climate cycles that occur, which obviously won't have occurred much over the last 40 years. It wouldn't give you a very good sample size. And we also need to understand the impacts of climate change, which we understand some of the impacts, which I talked about earlier, but actually a lot of them we still have quite a lot of uncertainty on. And so this is why we use a stochastic event set in a CAT model. So this allows us to essentially look at the correlated risk associated with multiple hazards from an event. So if it's a TC, we can look at the flood risk as well as the flood hazard, as well as the wind hazard. And if we have a really large event set, it allows us to look at a full range of different climate states, so different phases of ENSO, for example. And then also, if we include physically based climate models in the modelling framework, we can represent the impacts of climate change on these hazards and really start to understand some of those future changes. Joshua has been through the full modelling chain in a bit more detail, but essentially we use the stochastic event set, which is millions of tropical cyclone events that RIAS could produce. They also have a wind hazard model that they've developed in-house, so they have the wind hazard that's associated with each of these events. We're developing a precipitation model with them so we can know what the rainfall is for each of those events, which we then run through our flood modelling framework to produce inland flood hazard. And then they can be linked to storm surge models to then produce the coastal flood hazards. And so it really allows you to properly understand the correlated risk from tropical cyclones and how that might change in the future for different climate scenarios and different time horizons. Next slide, please. So I'll just briefly talk about some of the use cases we see for this type of data from an engineering perspective. So there's a few different applications. I think more detail on this was covered in the second webinar in the series. So if you want to hear a bit more about that, then you can refer back to those, or obviously just get in touch with someone at Fathom and we can talk things over with you. There are a few different applications. So one is site selection. So it can be, this kind of data can be used for a detailed analysis of current and future risk, providing a consistent perspective across multiple existing and prospective sites. For linear assets, future hazard risk can be embedded in business planning or asset management. It can improve resilience assessment and then allow better prioritization of investment and adaptation planning. Critical assets such as airports and data centers and distribution hubs are all susceptible to the impacts of natural hazards. So understanding this risk now and over the full operational lifetime of the asset is necessary. And linked into all of these is finally the kind of climate analytics aspect. So different projects and applications might require consideration of different climate scenarios, different time horizons in the future. And uncertainty may also be something you're interested in, so kind of looking at different percentiles of future projections. So using a vendor model that allows flexibility in the climate change hazard assessment that you can look at may be really important. And so this is something that Fathom's climate dynamics framework, which we discussed in the second webinar, allows for. And it will also be something that our combined TC CAT model for the US, developed in partnership with RIAS, will also allow for. Right, last but one slide, next slide, please. Some key overall takeaways of kind of things that we've been through in this webinar. Compound risk modelling is a developing area of research, both in the academic community to some extent, but also more in kind of industry and how this research and this data can be applied. It's very dependent on local conditions, particularly meteorological and hydrological conditions. And most major weather and climate-related catastrophes are caused by compounding drivers. Under a warmer climate, compound events, and particularly TC-induced events, are expected to amplify in many regions. And it's really important that non-stationarity is considered in compound event analysis, because climate change will significantly influence the dependence and spatial temporal dynamics of these different drivers. And so we kind of advocate for the use of fully correlated hazard modelling approaches using high resolution climate models in conjunction with things like machine learning techniques, which can be really powerful in analysing some of these climate trends, particularly when you're looking at TC-induced compound events, because they're both spatially and temporally compounding in nature. So it's quite complex to look at how they work now and also how they might change in the future. Under climate change, next slide, please. So that concludes our webinar, so the third webinar of this series. So if you'd like more information, you can see our website here. You can also request a demo of Fathom's data by emailing info@fathom.global. As I mentioned previously, there's a couple of previous webinars that you can go and have a look at if you're interested in how we might go about doing global scale flood modelling, and also how climate change might impact flood risk globally. And if not, hopefully we have some questions in the Q&A box. If anyone would like to add any more, if any more come up to think, then yeah, please go ahead and add them. I'll invite Joshua back as well. I know he's already back, so that we can answer some. So we've got one. How are you implementing AI in your forecasting? What type of ML algorithms are you using, and what type of data are these models being trained on? Obviously, a high-level overview, not the nitty-gritty, would be appreciated. So in terms of, I guess I'll talk mostly about our partnership with RIASC, because this is the kind of the application for compound wind and hazard flood modeling that we're using this on. They have developed an AI TC track model, which is using random forest modeling. So they use observations and also climate model input to essentially seed different tropical cyclones, and that they've just run this over many, many years under different climate conditions, different climate states. And this kind of gives them this full ensemble of, or this full catalogue, sorry, of, you know, over 1 million different TC events. They've also used a similar methodology in their wind hazard model, and then also their precipitation model. So they've run what's called the WRF model, so the WRF model, which is a really high resolution weather model. So they've run 200 tropical cyclone events, I believe, at a 1 kilometer resolution, which they then use to kind of construct the wind and the rainfall fields for this full ensemble, this full catalogue of more than 1 million different TCs, and that gives us this kind of stochastic event set that is used. They also use ERA5 data as well, so they kind of use a combination of ERA5 data and then also climate model data as well.
And just to add to that as well, if for anyone interested in, I guess, the machine learning methodology in greater detail, you can check out the paper Lordan et al. 2017, Machine Learning Approach to Modeling Tropical Cyclone Wind Fields, which goes into detail on the creating those synthetic event sets.
Yeah, thanks, Joshua. I think there's one for you in the Q&A, Joshua, about your flood review paper.
Oh, let's see. The paper, it's currently in preprint. I believe we'll be sharing the presentation slides, and there's a link in the slides. If not, I can post it in the chat. It's currently just a preprint, but it should be out hopefully by the end of the year. Let's see.
Right, so we've got one, how do the interactions between multiple extreme events affect the accuracy and reliability of return period estimates, particularly for events like 10,000 a year? Do you want me to take that, Joshua, or do you want to take it?
Sure.
Cool, I will take it. So yeah, so it obviously does have an impact. So that's one of the key reasons why we need the use of stochastic event sets. If you're only using 40 years or even 100 years of observations to look at these kind of events and trying to calculate return periods, there are statistical methods that can be used, like extreme biodistributions and things, which can kind of try and estimate what the very high return periods might be based on those observations. But obviously the uncertainty associated with those is pretty large. And so that's why you kind of need the stochastic event set, which allows you to kind of better and hopefully more accurately estimate what those kind of return periods might be, and also better represent the tails, so those really, really extreme events, have a better understanding of what they might look like, how severe they might be, and what the hazards with those associated with those might be as well.
I see one more question about management practices related to compound flooding and nature-based solutions. Overall, for compound flooding, I would say the management aspect, what you're going to do is you want to look at the areas where compounding is most likely to occur. So this differentiates from regular flooding in that you're looking at where the flood drivers are interacting. So you have to examine where is this happening, maybe where to prioritize management practices, whether that be defense. For example, if you can also look at things like what drivers are dominant. So maybe in one situation, you have interaction of rain and coastal processes, but say if you have heavy rainfall, maybe you want to look at water storage or drainage facilities, whereas maybe if the tide surge or sea level component is the larger aspect of the compounding, then look at storm surge barriers or natural management like seagrass, mangroves. So it really comes down to looking at where it can be implemented, and also do existing defenses account for compound extremes. Currently, many flood defense around the world only look at extremes of individual drivers, but there's always the possibility that if you've multiple interacting, then maybe a flood barrier was only designed to look at a certain 1 in X year wave event, but maybe that isn't really accurate if you're also including like river discharge. So for management purposes, it's really important to look at or consider the compounding aspect.
Great, thanks. There's also a question on the influence of terrain, so whether models are sensitive to land use, things like deforestation, urbanization, loss of mangrove fringes and coastal squeeze. The answer would be yes. It is somewhat difficult to represent very high resolution kind of representations of some of these things in different stages of the modeling methodology. So the climate models, for example, because they're run either globally or regionally, and we talk a bit more about this in the second webinar, but they're run at relatively low spatial resolutions compared to impact modeling. So it might be a grid box will maybe be sort of 25 to 50 to 100 kilometers, just because the climate models are so complex and are run on supercomputers, and so you kind of have to make some compromises somewhere, and that might be in the kind of spatial size of the grid boxes. So they might include some representation of things like deforestation in urban areas, but obviously like loss of mangrove fringes and things would be far beyond what they're capable of representing. Having said that, the precipitation and wind and also the coastal surge modelling is done at a much higher resolution, because obviously the impacts, to properly represent the impacts of these events, you do need this kind of high resolution. I can't off the top of my head remember the resolution of our coastal model, but I know it is, I don't know if Josh
should be 30 meters.
30 meters, okay, yeah. So it will include some of those kind of really smaller scale changes in like the coastal landscape and rivers and things, so be able to represent some of those dynamics. Things like loss of mangrove fringes and land use on the coast isn't something that we kind of represent changing over time, again just because the uncertainty is kind of so high related to some of these things. But on a very local level, it may be that that they do have an impact. But yeah, once you're kind of trying to model over large regional scales and global scales, it does become quite difficult to really represent some of these these very, very small scale localized processes. And then so far, there's one more final question. How does this differ from the most popular models, such as from the Met Office and CIWEM? So I guess they're different models for different applications. So I think if you're talking about the Met Office and the ECMWF, I imagine you're talking about the kind of forecasting models that they use, the very high resolution models, which they might run over days or weeks to look at how weather might change. We're more interested in the kind of longer scale changes in climate or seasonal changes. And it's kind of those types of models, so climate models, weather models at the beginning of the framework, but then you have to feed that through into through kind of multiple different stages that Joshua went through in order to get to that hazard, to that impact. So you have to take the rainfall from events such as that and then feed that through to look at how that might impact river levels, whether pluvial flooding might be associated with that, how the wind and the intensity of a storm and event, for example, might drive a storm surge, how far inland that storm surge might propagate, and then what the hazard is associated with that. So those kind of weather and climate models are the very top of the modelling framework, and then you have to follow all the way through the process in order to get to the impacts and the hazard. And then Evie has just mentioned in the Q&A, on a side note and more general background, the United Nations apparently is running a free course which closes on September 1st called Water Addressing the Global Crisis. So I guess if anyone is interested in that as well, then then go and check that out. I think we'll leave it there because that's most of the questions answered. But if anyone thinks of any questions that they haven't thought up and would like to get in touch, then please email us at Fathom and we can get in touch. And then any questions that haven't been answered, we can follow up with afterwards, although I think the majority of them have been answered. So thank you very much for joining us. There will be a recording of this available. So if there are any slides or any bits that you want to go back and refresh your memory on, then please do look out for that. And if not, thank you very much for joining us. Thank you, Joshua, for joining us, and we hope you've enjoyed the webinar.